Ho Aeon Millen, hello, and this here is my next video. I did kind of promise that I would say, I would show you guys how to do this math step by step. So in the notes for this video, I'm going to have what I'm going to go through in there so you can walk along the process as well. And you can see where it correlates to the paper as well. A lot of this here is going to be in paper too. So, all right, first and foremost, step one. Let me take everybody back in time a little bit to when Einstein came up with general relativity. All right, he had an equation that was validated, that worked, that showed that space was something. It showed that it had curvature and that it would curve light around objects and such. So he had his balanced equation. Then they discovered the cosmological constant. So the next step is to take general relativity. Okay, they're going to add lambda to it because of the expansion. So the lambda term was added to the geometric side of the equation. All right, now they have been looking at that term, and that led to one of the biggest crises in cosmology. They didn't understand why it had such a huge order of magnitude possible, and yet the actual value of it was nothing close to it. So let me explain why. The next step, you got to actually add the inverse additive to the other side of the equation. It is an absolute law of mathematics. They didn't do it. Now, if they would have tried to do it back then, like I said in one of my other videos, they would have never been able to figure it out because it would have just been another term on there, and they wouldn't have had anything to understand what those terms represent. You have the pressure outwards, and then you have the cutoff that keeps it from going faster. It's a maximum speed limit, so to say. It's a cutoff energy tensor. So once we do that, it's the saturation function. It prevents an infinite elasticity and singularities. It, in essence, turns space into a cup. It gets filled, and it locks up. It makes a particle of pure space. You can't put anything else in it because it's full. Anything else that goes on top of it has to go to the outsides. So, and it gets larger and larger from there. We see the three-dimensional shadow of a six-dimensional object in space. And so that gives you, once you actually go step by step and put those terms together, as it shows for the saturation function, because there is a couple of more steps from that. It's not just that step. But once you put those terms together and complete the math, it turns into step 5, which is the final saturated field equation by substituting the standard Einstein tensor back to the left side for simplicity and replacing the standard cosmological constant with the new saturation term. We arrive at the finalized equation shown in the first document. So, and the reference pages for that 51 and 52, sections 21.3.3, for any of those who want to go ahead and dig into that deeper. And then I have a term-by-term expansion or explanation here as well with the Einstein tensor, the vacuum yield point, the curvature scalar, the saturation function, the metric tensor, Einstein's constant, and then the stress energy tensor. It really came down to it being as simple as they just needed to understand that final term. So, but it really was as simple as that. Now let me explain to you what those terms are. That'll be the next part of this. All right. So deriving the vacuum yield point, the origin of lambda plus and minus, the principle of the additive inverse, the realization that lambda requires both a positive and a negative component comes directly from the rules of quantum field theory and particle spin statistics. Every field mode contributes to the vacuum energy, but the sign of that contribution depends strictly on the particle's spin. So they have a positive term and a negative term. Okay, to have a mathematically sound field equation, you cannot violate the balancing principle by only adding the positive bosonic energy. You must explicitly include the fermionic subtraction. It's math. Who would have thought? But sometimes when your head's full of all the dogma and all the ways that people were telling you it can't be done, it's no wonder they missed it. All right, step 2, identifying the actual physical agents of the Higgs, or I should say the Higgs and the top quark. Once the mathematical requirement for a positive and negative balance was established, the physical particles responsible for the standard model had to be identified. So the positive anchor is the Higgs. It provides the baseline positive potential, trying to keep the vacuum stable. Prior to its mass being discovered in 2012, physics was missing the boundary condition required to solve this problem. So give yourselves a break. It's okay that you didn't see it, but I'm showing it to you. Next, the negative anchor, because it's anomalously heavy. The top quark they don't really have an explanation as to why it's so heavy. Well, we kind of do. It completely dominates the fermionic sector. It acts as a physical agent for the additive inverse, and it provides a massive negative mathematical pull that directly fights against the positive potential of the Higgs. It's the balance, it's the other side. It keeps it from going too fast. You know, if it wasn't for that interplay, space wouldn't either. If we don't have the cutoff lambda negative or whatever, space would have just flown apart faster than the speed of light. It would have just accelerated like they're trying to say, but that's not what we see. There's things move at a finite speed. So that's why. Determining the yield point. Now, to find exactly where the vacuum settles or yields, we have to look at how the stiffness of the vacuum changes as energy increases, which is governed by the renormalization group equations, RGE. This creates a literal mathematical tug of war. The vacuum's effective potential, the bosonic contribution, tries to keep the coupling positive, stable, while the heavy fermionic contribution of the top quark drives it negative to instability. The yield point is the exact energy scale where this coupling crosses zero. So that's where that term came from, was analyzing the difference between those two terms. And then what you see is at this precise point, the negative pull of the top quark perfectly cancels out the positive stability of the Higgs, signaling the complete breakdown of the vacuum's elastic restoring force. By plugging in the measured masses of the Higgs and the top quark, integrating the equation reveals that this crossover point occurs right at 10 to the 11th giga electron volts. Okay, that's how the math worked out. This is how the fundamental structure limit of the vacuum is definitively set. And that came from experiments. That came from accepted science. And that's why. So I'm going to have that in the comments. Again, I'm going to have this entire little lesson plan in the comments for you guys to read through. So on page 42, section 18, 4.2, the missing boundary conditions. Pre-2012, the core reason, physics simply did not have all the required puzzle pieces until 2012. Okay, they were missing a variable for one, the Higgs mass. Okay, they had to get that. And in order to calculate the exact structural limit of the vacuum, you need to know the mass of the particles doing the pulling and pushing. So that didn't come until 2012. Without knowing the exact mass of the Higgs, it was impossible to define the structural limit of the container. You can't find the exact point where a balanced equation crosses zero if you only know the value of one side. Once the 125 gigaelectron volts mass was confirmed, the missing boundary condition was finally established. And the resulting calculation, only with both the top quark and the Higgs, we could then mathematically pit them against each other, and that's where we got the scale for 10 to the 11 gigaelectron volts. Before 2012, anyone trying to complete this math was essentially trying to solve an equation with a blank variable. So, but it was as simple as that. So, take as much time as you need. It is technically the Holy Grail of physics. That's what they've been looking for. A way to figure out how quantum mechanics and general relativity merge together. So once you understand how the standard model fits into that picture, which we got with the Higgs, we just put the math together. So, and yeah, I needed a calculator to do it because people don't like to listen. So let me just make that very clear. A lot of people do not like to listen when you're telling them how to correct themselves. I get it. So it's fine. But if you have any other questions or anything, feel free to ask them in the comments. I appreciate you guys watching. And I hope this is informative to you guys so you guys can see exactly what we need to do to get this whole picture cleared up. So stay blessed, people, and ho aeon melon. This is Joe signing off. Have a good day.